Welcome again to the video lecture class. I hope you all are well, and I hope you have seen that video on fundamental theorem of arithmetic. That was quite interesting video. That's why I had shared that with you. So I hope you all have understood that. So I'll quickly go through this theorem. See, this is your theorem 1.2 fundamental theorem of arithmetic. The statement says every composite number can be expressed factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Right? So don't get confused by so much of scientific words and all use. This is very much simple. See what it says. It says that, see, this is 91. 91 can be written as 7 multiplied by 13. Also, you can write 13 multiplied by 7, right? So 91 is a composite number because it is having factors 1, 91 as well as 13 and 7. Factors more than 2 are composite numbers that I had already discussed in my very first presentation. So this will be your composite number and it can be written as 7 multiplied by 13 or 13 multiplied by 7, vice versa, right? So if you take 455, 455, so this can be written as 5 multiplied by 7 multiplied by 13, or you can write 7 multiplied by 13 multiplied by 5, or you can write 13 multiplied by 5 multiplied by 7, whatever order you want, right? But using 5, 7, 13, whenever you multiply these numbers, you will be ultimately getting 455 only, right? So what they say that these product of these primes is unique, right? And apart from the order in which the prime factors occur, no matter what the order is, but when they are multiplied, you will be getting the same number, right? So this is your fundamental theorem of arithmetic. So I hope you have understood that. Now we'll move on to this. Okay, just out of curiosity, I would like you all to just go through this immense personality, Carl Friedrich Gauss. He's the prince of mathematicians. He's also referred as prince of mathematicians. In fact, he means Gauss, Archimedes, and Newton. These three people are very great mathematician and physicist as well. So, out of curiosity, you can search about his inventions and all, right? So now we should now move on to one more interesting line that has been mentioned, that prime factorization of a natural number is unique except for its order. This is the same statement which you got in your theorem, right? So see, whatever the values, right? We are having a bigger number, 32,760. 2 1 2 multiplied by 2 multiplied by 2, see how many times? 3 times, and 3 is 2 times, 5 1 7 1 and 13 1. Now for our understanding and for better representation, how can we write? We can use exponents as well. So we can write 2 to power 3 multiplied by 3 to power 2 multiplied by 5 multiplied by 7 and multiplied by 13, right? So I can write it in any order which I want, right? In any order which I want, but whenever I multiply these numbers, I will be getting this number only, like 32,760 I'll be getting, whatever order it is written here, right? But for our understanding and for better representation, how we write it in ascending order, right? Ascending order. So as you know, 2 is the smallest prime number, so 2 is written at first, then 3, then 5, and you know the sequence, right? Okay, so this is how you write, and whatsoever the power is, you write it here, right? And so on. Okay. So now coming to example number 5, consider the numbers 4 to the power n, where n is a natural number Now we have to check whether there is any value for n for which 4 to power n ends with digit 0. Now with digit 0 means at the units place you are getting 0 at the units place, or the ones place if you say ones, all are the same, right? So look at the solution. If the number 4 to the power n for any n were to end with digit 0, then it would be divisible by 5, right? You know that if you divide 10 by 5, you can very well get a whole number, right? So to end with 0, it would be divisible by 5. So that is the prime factorization of 4 to power n would contain the prime 5. That means it should contain 5 as a prime factor. So is this possible? Obviously not. This is not possible because 4 to power n, say suppose 4 is equals to 2 multiplied by 2, right? And 2 multiplied by 2 is 2 to the power 2. And if it is n here, 4 to power n, that means you are getting 2 to the power n. Nonetheless, in none of the condition you will be getting 5 as the prime factor, right? So the uniqueness of the fundamental theorem of arithmetic, what it does, it guarantees that there are no other primes in the factorization of 4 to the power n, right? You are not having any other factors, so there is no natural number n for which 4 to the power n ends with the digit 0. You are getting only 2, right? So this is false. Now next is example number 6. Now just look at this example very carefully. You will be getting one formula here to calculate LCM and HCF of two numbers, sorry. Find the LCM and HCF of 6 and 20 by prime factorization method. See, prime factorization method, you write it in the factors form, right? 6 can be written as 2 to power 1 and multiply by 3 to power 1, and 20 can be written as 2 to power 1, yes, 2 to power 1, 5 to power 1, like 2 to power 2 multiplied by 5 to power 1. Right, if you are having trouble in writing this prime factorization all of a sudden, what you can do, you can very well write, you can use your previous methods that you used. So this you will be getting, then this you will be getting. If anyone is facing troubles, so I'll suggest you to not to do wrong calculation, rather calculate these things in rough, right? So you will be getting the prime factors. Now you can find the HCF of 6 and 20. How? 2, the smallest one. See how you're calculating the HCF is, here is 2 to power 1 multiplied by 3 to power 1, and this is 2 to power 2 multiplied by 5 to power 1. So the highest factor which is common in both of them, is what? Only 2 is common, and that too only one time. So 2 to power 1. So your HCF 2 to power 1 is ultimately 2. So your HCF is 2. And LCM is the lowest common factor. So lowest common factor is, see, lowest common factor will be 2 with the maximum power is 2, right? 2 and 3 and 5, right? So this is what? This is 60. You got it here only. So this is your LCM, right? Now from this we are getting one formula as well that product of the smallest power of each common prime factor in the numbers. This is HCF. Smallest power of each common number. Smallest power means this is the only common number, right? This was the only common number. For HCF, I'm telling you that this was the only common number and the smallest power was 1, right? So this is your HCF, right? Now for LCM, the product of the greatest power of each prime factor involved in the numbers. Like each factors, right? Each factors, right? Okay, so 2, 3 and 5. These three numbers are involved in both of these numbers. So you will be writing 2, 3 and 5. And the highest power for 2 we are having, among these we are having 2 as the highest power. So we have written 2. Among these we are having 3 to power 1 means power of 3 is maximum 1 here, and 5 to power 1 maximum power of 5 is 1, right? So this is your LCM, and after calculating this you will be getting 60, right? So from the above example you might have noticed that LCM multiplied by HCF multiplied by LCM is 6 multiplied by 20, right? In fact, we can verify that for any two positive integers a and b, HCF multiplied by LCM is equals to a and b. See, this is nothing but, I'll write it here. This is a very easy phenomenon that happens. So this is the numbers were 6 and 20, right? And what you got? Okay, let me write it in the form. If the numbers are a and b, your LCM and HCF, the product of your LCM and HCF are equal to the product of the numbers you have taken. So what you have taken here, you have taken 6 multiplied by 20 and you got LCM. What was your LCM? LCM was 60 and your HCF was 2, right? So you will be getting 120 equals to 120. So from this you can get that the product of the two numbers is equal to the product of their LCM and HCF, right? So this is one thing that you will be applying in the upcoming exercise. Now similarly for example number 7, find the HCF of 96 and 404 by prime factorization method, right? So after prime factorization, 96 can be written as 2 to power 5 multiplied by 3. 2 to power 5 multiplied by 3 for 95. And for 404, what they got? They got 2 to power 2 multiplied by 101, right? So for HCF, what I had told you earlier, for HCF, the common number, what is the common number in both of them? The common number is 2. You are having 2 in both, 2 as a factor in both of them. So right, 2 and the smallest power is 2 as well. So 2 to power 2, that is 4 will be your HCF, right? And in case of LCM, you are getting 2 common, so write 2, then 3, then 101. So all the prime numbers are used here. Now use the highest power. Highest power of 2 is 5, right? And highest power of 3 is 1 and highest power of 101 is 1, right? So this is one way to calculate the LCM. 2 to power 5 will give you 32, then 3 into 3 is 101 will give you 303, and you can calculate this and you will be getting 9696, right? This is one way. And another method is easier, I guess, because that can decrease this calculation. So how will this decrease your calculation, right? So a multiplied by b is equals to HCF of these numbers and LCM of these numbers. What you wanted to find out? You wanted to find out the LCM, right? So you can ultimately take this HCF there and divided by HCF, right? So here you can get 96 multiplied by 404 divided by the HCF. So 96 multiplied by 104 divided by 4. So we'll be getting LCM, right? So this is the easier method. See, both are easy, but that depends upon the number you are getting, right? So you just check out for the numbers. If they are easy to calculate, you can find it from this method. If they are a bit typical, or you think that after division it will be easier, so you can use this method as well, right? But you should know both the methods. Okay, so this was for example number 7, and now I'll move on to example number 8. Example number 8, find the HCF and LCM of 6, 72 and 120, right? Using prime factorization method. So see, whatever I have taught you, this formula till now, this is possible only for two numbers, right? You cannot apply this here for 3 digits. We are having another kind of formula for these three numbers, right? So for this, you will be finding out the LCM and HCF separately from this method, right? So 6, you can write it at 2 multiplied by 3. 72 can be written as 2 to power 3 multiplied by 3 to power 2. 120 can be written as 2 to power 3 multiplied by 3 multiplied by 5, right? So this can be written as here, and now here 2 to power 1 and 3 to power 1 are the smallest powers of the common factors. See, you can very well see here that 2 is common, so you can write 2, and 3 is also common, so you can write 3. Now the smallest power is 1, so 1, and for 3 it is 1. So 2 to power 1 and 3 to power 1. So if you multiply this, you can get 6. 6 is the HCF of 6, 72 and 120, right? And for LCM, you will be writing the factors 2, 3 and 5. These were the numbers that had been used, prime numbers that has been used. So you will be writing 2, 3, 2, 3 and 5 with the highest power. So highest power for 2 is 3, and for 3 is 2, and for 5 is 1, right? So 2 to power 3 is 8 and 3 to power 2 is 9, and this is 5. So 40 multiplied by 9, so you will be getting 360, right? Sorry, you will be getting 360 as LCM, right? Here it is written. So this is for this class. Next class I'll be taking exercise 1.2. So till then, stay safe, stay at home and keep studying. Thank you so much, class.